In this video, we will take a look at how you write a chemical formula. When you're given a name, for example, calcium sulfide, what you're going to do is go to the periodic table, look up the symbol for calcium. Calcium is +2, and it has a +2 oxidation state. Sulfur is -2. Remember, the IDE just indicates that it's a negative ion here. Next, what you'll do is you'll crisscross your charges, dropping the positive and negative. You don't longer need them. And you'll just write Ca2S2, which can cancel out. You just end up with CaS. Give you another example would be magnesium chloride. Look up the symbol. Mg is +2, chlorine is -1. You crisscross, you get Mg1, which you don't need to write, and Cl2. This you cannot reduce any further. When you cannot reduce the formula any further, it's called an empirical formula. Okay, let's try a polyatomic ion. How about magnesium phosphate? Remember that when something ends in ate or ite, as well as hydroxide and cyanide, can be found on table E. So magnesium is +2, phosphate is PO4 3-. You would crisscross the charges, you get Mg3, PO4 2. But remember that when you have a polyatomic ion, you're trying to show the whole thing gets the -2 charge, so the whole thing is going to go in parentheses. Similarly, if I had calcium hydroxide, I look up the charges. Calcium is +2, hydroxide is -1. Crisscross, Ca gets the 1, which we don't have to write. And the OH has to go in parentheses to show that the whole polyatomic hydroxide is a 2. There are 2 of them. Let's look at another type of example where we have a transition element. How about iron 3 oxide? The 3 tells me which charge of iron to use. Iron is a transition metal and has more than one oxidation state. So this is telling me to write the charge +3. So the Roman numeral will always indicate the charge of the metal. Oxygen is -2. We crisscross and get Fe2O3. Now I'll show you one more example of something a little bit more difficult. Titanium IV oxide. Titanium, charge of the metal, is +4. Oxygen is -2. When you crisscross, the molecular formula gives us Ti2O4. We can reduce this, however, so we get TiO2 as our empirical version of the molecular formula.